Imagine that you buy a high-precision watch, a jewel of engineering designed to last decades. Upon receiving it, the manufacturer hands you a manual that says it never needs oil or only change the parts every 5 years. You obey, you trust the brand, and right at the 6th year, the watch stops forever. Was it an accident? No, it was a legal murder. In the motor world, exactly the same occurs. There exists an abysmal gap between what your engine needs to survive and what the user manual says that you must do. The manufacturers do not lie, but they omit. Their priority is not that your car reaches 500,000 kilometers. Their priority is that the maintenance cost appears low during the first 3 years to seduce the big renting fleets, and that, once the warranty is finished, you return to the dealership for a new model. Today we are going to break the code of silence. We are going to enter the dark zone of the workshops to reveal why phrases like lifetime oil or intervals of 30,000 kilometers are the death sentences of your camshaft and your turbo. Prepare yourself, because we are going to analyze from the chemistry of the acids in your crankcase to that small habit that 90% of drivers commit when turning off the engine, and that is decapitating their crankshaft at this precise instant. Welcome to the silent agony of your engine. We begin. Error 15, the myth of the 200,000 kilometers and the collapse of the TBN. The most legal and accepted error in the world is the extended oil change interval. They have sold us the idea that modern synthetic oils are indestructible magic fluids. But chemistry does not lie, and oil is, by definition, a sacrificial component. When the oil circulates through your engine, it not only lubricates, it acts as a cleaning agent, a coolant, and a hydraulic seal. The first factor that kills the oil is not the use, but the oxidation. At operating temperatures, oxygen reacts with the hydrocarbon chains of the oil, creating organic acids and sludges. However, the true silent killer is the collapse of the TBN, the total base number. The TBN is the alkalinity reserve of the oil. It is what neutralizes the corrosive acids that are formed during combustion, especially when the sulfur from the fuel mixes with condensed moisture. When you stretch the change to 20,000 kilometers, the TBN often reaches zero much sooner. In that moment, the oil becomes acidic. It stops protecting and starts to eat the soft metals of the connecting rod and crankshaft bearings. Modern oils are multi-grade, which means they use viscosity index improvers, 7. These are long-chain polymers that expand with heat to prevent the oil from becoming too thin. Imagine them as microscopic springs. In a high-compression or turbocharged engine, these polymers pass through zones of extremely high pressure, such as the camshaft lobes or the piston rings. This mechanical stress physically cuts the polymer molecules in a process called shearing. An oil that started as a 5W30 after 15,000 kilometers of mistreatment may have sheared until becoming a 5W20 or even less. The result is a lubricating film so thin that it allows metal-to-metal contact. When the dispersant additives become saturated, they can no longer keep the soot and carbon residues in suspension. These residues begin to precipitate and stick in the low flow zones, such as the oil pump strainer. The legal maintenance of the dealership rarely mentions that, although the oil holds up, the oil filter usually collapses much sooner. When the filter becomes clogged, the bypass valve opens, and your engine starts to circulate dirty and unfiltered oil directly to the most critical parts. You are sanding your engine from the inside while you believe that you are saving money. Error 14, the cold start and the boundary lubrication. If you have ever turned on your car and shot off immediately, you have committed a capital sin against thermal physics. 70% of the total wear of an engine occurs in the first 60 seconds after starting. At ambient temperature, even the best synthetic oil is thick compared to its state at 100 degrees. Kinematic viscosity determines how fast the oil can travel from the crankcase to the cylinder head. In a cold start, there is an interval of time, sometimes of several seconds, where the valve train is operating in what we call boundary lubrication. In this state, there is no oil layer separating the parts, only a microscopic molecular layer of anti-wear additives, such as ZDDP, remains. If you demand load from the engine in this state, you are allowing the metal to scrape directly against the metal. Here enters the physics of materials. The pistons are usually of an aluminum alloy, while the block or the liners are usually of cast iron or have Nicosil/Alusil coatings. Aluminum has a much higher thermal expansion coefficient than iron. This means that, when cold, the piston is physically smaller than it should be to fit perfectly in the cylinder. It has an excessive play or clearance. If you accelerate hard, the piston heats up much faster than the cylinder walls, which are surrounded by cold coolant. The piston expands violently before the cylinder has space for it, causing the phenomenon known as piston slap or, in extreme cases, micro welds between the piston skirt and the cylinder wall. The crankshaft floats on a hydrodynamic oil wedge. For this wedge to be stable, rotational speed and a specific viscosity are needed. At startup, that wedge does not exist. The crankshaft physically rests on the bearings. Every start is a hammer blow for these metals. Not warming up the car does not mean leaving it 10 minutes at idle, which is another error we will see later, but allowing 30 seconds of circulation and driving with extreme smoothness until the oil, not the water, reaches its operating temperature. Ignoring this is reducing the life of your compression rings by half. Error 13, the electrolysis and the eternal coolant. Coolant is the most ignored fluid of the entire vehicle. Many believe that as long as the level is okay and the car does not heat up, everything is correct. Fatal error. Modern coolants use organic acid technology, OAT. Unlike old silicate coolants that covered the entire system with a protective layer, OATs only react chemically when they detect a corrosion point. The problem is that these chemicals have a useful life. Over time, the coolant becomes acidic. When the pH of the coolant falls below 7, the fluid becomes an electrolyte. The engine essentially becomes a giant battery. This process is called electrolysis in an engine where metals are mixed, iron block, aluminum head, copper or aluminum radiator. Electrolysis causes ions to move from one metal to another. The weakest metal, anode, begins to disintegrate. That is why we see water pumps with the blades totally disappeared, as if something had eaten them. It is not physical erosion, it is pure chemistry. Furthermore, if the coolant has lost its surfactant properties, microscopic vapor bubbles occur in high temperature zones, around the combustion chambers. When these bubbles collapse, they generate a shockwave so powerful that it tears metal fragments from the block. This phenomenon, cavitation, can pierce a cylinder liner from the outside in, letting water enter the combustion chamber. Many drivers commit the legal error of refilling the system with tap water. Hard water contains minerals that, when heated, precipitate and form a layer of scale or lime inside the radiator and the block passages. Scale is an excellent thermal insulator. A layer of only 1 millimeter of lime has the same thermal resistance as several centimeters of steel. Your temperature sensor may mark normal because the water is at 90 degrees, but the internal walls of the cylinder could be at critical temperatures because the heat cannot jump the lime barrier to reach the coolant. You are cooking your engine in its own juice without knowing it. Error 12, the octane fraud and the LSPI. The manual says that your car can use 91 octane gasoline, or regular. What it does not tell you is that this recommendation is the legal minimum, so the car does not break today, not the ideal, so the engine is efficient and durable. Octane is not a measure of power, but of resistance to auto-ignition. In a modern engine with direct injection and turbocharger, the pressures inside the cylinder are brutal. If you use a low-octane fuel, the mixture can explode before the spark plug fires, or even after, creating a second flame front that crashes against the first. This generates a supersonic shockwave that hits the piston like a steel mallet. Most modern cars have knock sensors that retard the ignition timing to protect the engine, but here is the trap. By the time the sensor detects the hit and adjusts the electronics, the damage has already occurred. Thousands of micro-hits over years end up cracking the ringlands of the pistons. This is the error that is killing small turbocharged engines, downsizing. LSPI occurs at low revolutions and high load. In that moment, a drop of oil or an incandescent carbon particle can ignite the mixture prematurely. Unlike normal knocking, LSPI generates pressures so extreme that they can break a connecting rod or destroy a piston instantaneously. Low-quality gasolines or those with mediocre additives favor the creation of these carbon deposits that act as hot spots. Many people think, I use cheap gasoline and the car goes well. What they do not see is the high cycle fatigue. Engine components are designed for a smooth pressure curve. Detonation caused by suboptimal fuel changes that curve for a violent peak. Metal has memory. Every time there is a light detonation, micro cracks are created in the crystalline structure of the connecting rod. One day, without warning and without the engine having overheated, a connecting rod decides to say enough and comes out through the side of the block. The saving of a few cents per litre at the gas station just cost you a $10,000 engine. It is the perfect example of why the legal and the cheap usually is the most expensive in mechanical engineering. Error 11. The lifetime sealed transmission. The contemporary automotive industry has coined a term that should be considered a crime against mechanical engineering: lifetime sealed transmission fluid. World-renowned gearbox manufacturers like ZF or Aisin deliver units to vehicle brands with technical manuals that clearly specify service intervals every 60,000 or 80,000 kilometers. However, when that same gearbox is installed in a luxury or mass consumption vehicle, the automobile manufacturer communicates to the customer that it needs no maintenance whatsoever. This contradiction is not a communication error, it is a design strategy for the end of useful life. To understand why this is a catastrophic error, we must analyze the chemistry of automatic transmission fluid. Unlike engine oil, transmission fluid is a highly complex hydraulic oil that must fulfill contradictory functions. On one hand, it must lubricate planetary gears and bearings to reduce friction. On the other hand, it must provide the exact friction so that the multi-disc clutches engage without slipping. Over time, the extreme heat generated by the torque converter initiates a process of thermal oxidation. The molecules of the fluid break down, losing their kinematic viscosity and their capacity to manage heat. The true damage occurs at a microscopic level with the friction discs. These discs are coated with a cellulosic and ceramic material that, with normal use, sheds fine particles. In a transmission with maintenance, these particles are captured by the filter and the magnets of the pan. In a lifetime sealed transmission, the fluid becomes saturated with this abrasive material, effectively becoming a polishing paste that circulates through the entire system. This abrasive suspension begins to wear down the aluminum walls of the valve body. The valve body is the hydraulic brain of the transmission, full of small channels and pistons called solenoids that control gear changes with millisecond precision. When the fluid is dirty and oxidized, the solenoids begin to suffer from varnish deposits. Varnish is a byproduct of thermal degradation of the oil that adheres to metal surfaces. A solenoid with varnish becomes slow or gets stuck, which causes harsh gear changes, slippage, and finally, the total overheating of the unit. By the time the user notices the transmission fails, the damage is no longer solved with an oil change. The clutches have burned and internal tolerances have been lost forever. Accepting the myth of eternal fluid is accepting that your transmission will die as soon as the vehicle warranty ends. Error 10. The pressure washing and capillarity. There exists a dangerous belief that dictates that a clean engine is a healthy engine, which leads thousands of drivers to use high-pressure washing machines directly on the engine bay. This act of superficial aesthetics ignores the laws of physics and electronic capillarity. Modern electrical connectors are designed with rubber seals called O-rings, intended to resist environmental humidity and light splashes, but they are not designed to withstand a water column at 150 bars of pressure. When pressurized water hits a connector, the force is sufficient to overcome the rubber seal and inject moisture inside the plug. Once the water enters, it cannot leave easily. This is where the phenomenon of capillarity and galvanic corrosion begins. The water begins to travel through the internal filaments of the copper wires, moving away from the original connector and heading towards the electronic control unit, or ECU. In a matter of months, the copper reacts with the moisture and mineral residues, creating a substance known as green corrosion or sulfation. This green layer increases electrical resistance, interrupting the millivolt signals from critical sensors such as the crankshaft or the air mass sensor, causing ghost failures that are almost impossible to diagnose. In addition to the electrical risk, pressure washing imposes a brutal thermal stress on mechanical components. If you decide to wash the engine after having driven, the exhaust manifolds and the engine block will be at temperatures exceeding 200 or 300 degrees Celsius. By projecting cold water onto these cast iron or aluminum surfaces, an instantaneous thermal shock occurs. The sudden contraction of the metal can generate microcracks invisible to human eyes but structurally lethal. Exhaust manifolds can warp, breaking the mounting studs, or even the engine block can suffer internal stresses that compromise the tightness of the gaskets. A dirty engine is simply a sign of use. A pressure-washed engine is an electronic and structural time bomb that sooner or later will take its toll in the form of short circuits and unexplained leaks. Error 9. Solvent additives and seal drying. In the eagerness to clean the engine without disassembling it, many resort to the indiscriminate use of powerful solvent additives, often based on compounds such as acetone, toluene, or industrial alcohols. While these chemicals are excellent for dissolving hardened carbon deposits, they are mortal enemies of elastomer chemistry. A modern engine is full of seals, gaskets, and hoses manufactured with specific polymers such as Veton or nitrile. These materials are designed to resist hot oil, but not to withstand aggressive solvents that extract plasticizers from their molecular structure. When a solvent additive circulates through the system, it penetrates the pores of the rubber seals. Upon evaporating or mixing with the oil, it leaves the seal dry, rigid, and brittle. The result is a cascade of oil leaks that appear weeks after having used the miracle cleaner. But the most critical damage occurs in the forced induction system, specifically in the turbocharger. Solvents can literally decapitate the carbon deposits accumulated on the intake valves or in the turbo itself. Instead of dissolving smoothly, the carbon detaches in solid fragments. These fragments, hardened by years of heat, travel at sonic speeds towards the exhaust turbine. A turbine of a turbo rotates at more than 150,000 revolutions per minute. When a solid carbon fragment hits a turbine blade at that speed, the result is catastrophic. Even a microscopic impact imbalances the turbo shaft. An unbalanced shaft generates vibrations that destroy the hydrodynamic bearings in seconds, allowing engine oil to escape towards the intake or the exhaust. The irony is painful. In an attempt to clean and improve performance with a cheap solvent, the driver ends up destroying the most expensive component of the engine's air system. Chemical cleaning must be a controlled and professional process, not a backyard chemistry experiment that ignores the fragility of modern synthetic components. Error 8. The turbo coking. The phenomenon known as turbo coking is the perfect example of how a simple operating error can void years of advanced engineering. A turbocharger is a piece of engineering that operates at the limit of physics, with exhaust gases that exceed 900 degrees Celsius while the shaft rotates on a layer of oil of barely a few microns in thickness. The problem does not occur while the engine is on, but exactly in the second you turn it off after a prolonged effort. When you turn off the engine immediately after driving on the highway or climbing a slope, the oil pump stops instantaneously. However, the body of the turbo continues to radiate immense heat accumulated in its cast iron mass. The oil that remains stagnant on the turbo shaft stops circulating and remains trapped in a heat trap. In that moment, pyrolysis occurs. The oil heats up so much that its hydrocarbon molecules break and the carbon solidifies, becoming a hard crust known as coke. Every time you turn off the car in this manner, you are adding a layer of solid carbon to the turbo shaft. Over time, this layer reduces the clearance for oil flow and begins to act like sandpaper against the bearings. Eventually, the oil passages close completely. The turbo shaft runs out of lubrication and melts with the bearing due to friction heat. What manuals omit for marketing convenience is that a turbo needs an idling cooling period of at least 2 minutes after a trip. During this time, the fresh oil circulating removes excessive heat from the shaft, lowering the temperature enough so that when turning off the engine, the remaining oil does not carbonize. Ignoring this thermal cycle is, essentially, burning the lubrication system from the inside, transforming a high-quality oil into a solid residue that guarantees the death of the turbocharger long before the rest of the engine shows signs of old age. Error 7. Hygroscopic brake fluid. The braking system is, without a doubt, the most critical active safety component of any motorized vehicle, and yet its maintenance is the most ignored by the majority of users and workshops. The error resides in not understanding the chemical nature of brake fluid, which is a hygroscopic substance. This means it has a natural chemical affinity for water and possesses the capacity to absorb moisture directly from the air through the pores of the rubber hoses and the vents of the reservoir cap. Even in a perfectly sealed system, brake fluid can absorb up to 2% of its volume in water in just 1 year of normal use. This process is invisible but devastating. The first great danger is the drastic reduction of the boiling point of the fluid. A standard DUT4 brake fluid has a dry boiling point of approximately 230 degrees Celsius. However, When the water content reaches barely 3.7%, that boiling point falls dangerously to near 150 degrees Celsius. During a prolonged descent in a mountain zone or in emergency braking at high speed, the friction between the pads and the discs generates an immense heat that is transferred to the fluid. If the fluid contains water, this turns into vapor. As vapor is a gas and gases are compressible, unlike liquids, the brake pedal sinks to the bottom without offering resistance, a phenomenon known as vapor lock that leaves the driver without brakes at the most critical moment. But the danger is not limited only to the loss of braking power. The water in the system initiates a process of internal galvanic oxidation. The modern braking system is composed of a mixture of metals, aluminum in the master cylinder, steel in the lines, copper in some connections, and iron in the wheel cylinders. Water acts as an electrolyte that facilitates corrosion between these metals. This corrosion generates microscopic solid particles that travel through the system and end up lodging in the most expensive and delicate component, the anti-lock braking system, or ABS module. The ABS module contains a series of microvalves and an electric pump that must manage braking pressures with surgical precision. Rust particles act as an abrasive that scratches the internal walls of these valves or, in the worst case, blocks them completely. A single grain of rust can prevent a solenoid valve from closing correctly, which causes the car to pull to one side when braking or the ABS system to fail completely in a panic situation. Replacing an ABS module can cost thousands of dollars, an astronomical figure compared to the insignificant cost of changing the brake fluid every 2 years. Ignoring the hygroscopy of the fluid is to allow moisture to silently eat away the structural integrity of your brakes and the health of your wallet. Error 6. Driving on reserve and pump cavitation. There exists a deeply rooted habit among drivers that consists of waiting for the reserve light to turn on or even for the needle to touch absolute zero before visiting the gas station. This behavioral error ignores two fundamental principles of fuel system engineering: immersion cooling and fluid dynamics in confined spaces. In almost all modern vehicles, the fuel pump is submerged inside the tank, and this is not a matter of space saving, but of thermal management. The fuel pump is a high-speed electric motor that generates a considerable amount of heat during its operation. The fuel surrounding the pump acts as a giant heat sink, absorbing the thermal energy and keeping it at a stable operating temperature. When the fuel level drops too low, the pump is exposed to the air inside the tank. Air is a terrible thermal conductor compared to liquid, which causes the internal temperature of the pump motor windings to skyrocket. This excessive heat degrades the insulating varnish of the wires and deforms the internal plastic components, drastically shortening the useful life of the component. The second critical problem is the collection of sediments and cavitation. Although modern tanks are made of high-density polyethylene to prevent corrosion, the fuel itself can contain impurities, and condensed water always settles at the bottom due to its higher density. By constantly circulating with the tank low, the pump is forced to suck the fuel from the zone where the concentration of these contaminants is highest. Although a filter or pre-filter exists, the smallest particles can pass, acting as projectiles against the internal impellers of the pump. Furthermore, when the level is extremely low and the vehicle takes a curve or accelerates, the fuel shifts, allowing the pump to suck air momentarily. This generates a phenomenon known as cavitation, where vapor bubbles form due to sudden pressure drops. When these bubbles collapse near the metal surfaces of the pump, they generate shock waves with local pressures of thousands of atmospheres that can literally tear pieces of metal from the impellers. A driver who always circulates on reserve is condemning their pump to a slow death by overheating and mechanical erosion, transforming a part that should last the entire life of the car into a recurring and avoidable expense. Error 5. Prolonged idling to warm up. The ritual of turning on the engine and leaving it 10 or 15 minutes at idle in the morning before leaving is a vestige of the carburetor era that today results destructive for direct injection engines. In a cold engine, the electronic control unit orders an extremely rich mixture. That is, it injects much more fuel than necessary for combustion in order to compensate for the lack of heat and prevent the engine from stalling. The problem is that, at idle, the engine generates very little combustion heat and the oil takes an eternity to reach its operating temperature. During this prolonged period of rich mixture, the excess gasoline does not burn completely. Part of this fuel in liquid state hits the cylinder walls and washes the lubricating oil film that protects the piston rings. This phenomenon is known as cylinder wash and causes direct metal-to-metal contact at a stage where the engine is most vulnerable. Furthermore, that fuel that washes the walls ends up draining into the crankcase, mixing with the engine oil. This process is called fuel dilution and drastically reduces the viscosity of the oil, decreasing its load capacity and exposing the crankshaft bearings to premature wear. But the damage does not end with lubrication. An engine at idle never reaches the ideal combustion temperature for a clean burn. Low internal temperatures encourage the formation of black sludges, a pasty mixture of oxidized oil, condensation water, and carbon particles. These sludges begin to deposit in the narrow oil passages and in the oil pump suction screen, restricting the vital flow. For modern diesel vehicles equipped with particulate filters, prolonged idling is mechanical suicide. By not generating enough heat in the exhaust gases, the particulate filter quickly becomes saturated with soot. As the engine is not under load, conditions for automatic regeneration are never met, which ends up blocking the exhaust system and forcing costly manual cleanings or the replacement of the filter. The correct way to warm up a modern engine is to wait about 30 seconds for the oil to circulate and then start the journey smoothly. In this way, the engine works under load, generates heat quickly, the mixture becomes leaner in a few minutes, and the oil reaches its protection temperature much sooner, avoiding dilution and the formation of sludges that shorten engine life. Error 4. The myth of thick oil for old engines. There exists an old-school mechanical advice that states that, as an engine gains kilometers and starts to consume some oil, the viscosity must be raised, passing, for example, from a 5W30 to a 20W50. This practice, although it seems logical to reduce leaks or consumption, is a fatal error in engines designed with modern tolerances. Current engines are manufactured with micrometric precision, and their lubrication channels are capillaries, extremely thin to optimize oil pressure and flow. When we introduce a thicker or more viscous oil in an engine designed for a light oil, we are creating a massive flow restriction. Thick oil has a much higher resistance to movement, especially when cold. This means that, at the moment of startup, the oil takes much longer to travel from the crankcase to the highest part of the engine, the cylinder head or cylinder cover. The camshafts and hydraulic lifters are the first to suffer. By operating without oil pressure during those additional seconds every morning, the wear on the camshaft lobes is exponentially accelerated. Furthermore, many modern engines use variable valve timing systems that depend on hydraulic oil pressure to adjust valve timing. These systems use solenoids and actuators with orifices the size of a needle. An oil that is too thick cannot flow correctly through these orifices, which causes timing errors, loss of power, increased fuel consumption, and the eventual failure of the variable timing system, the repair of which is usually extremely expensive. Thicker oil also generates more internal friction, which raises the operating temperature of the engine. Contrary to belief, thick oil does not protect better at high temperatures in a modern engine. In fact, by flowing slower, it removes less heat from internal components such as pistons and bearings. The increase in oil consumption in an old engine is usually due to hardened valve seals or piston rings stuck by sludges, problems that are aggravated with a heavier oil. Following the manufacturer's recommendation throughout the life of the vehicle is the only way to guarantee that lubrication reaches every corner of the engine with the necessary speed and pressure to avoid destruction by dry friction. Error 3. Vacuum leaks and lean injection. In the delicate balance of internal combustion, the stoichiometric ratio is the absolute law. For a gasoline engine to work with efficiency, it must mix exactly 14.7 parts of air for every part of fuel. However, one of the most common errors in preventive maintenance is to ignore small fissures in the rubber hoses, the injector seals, or the intake manifold gaskets. These imperfections give rise to what we know as vacuum leaks, an unmeasured entry of air that occurs after the airflow or air mass sensor. When air enters the system without being accounted for by the vehicle's computer, the mixture becomes lean, which means there is an excess of oxygen and a deficiency of fuel. At first glance, a careless driver might think this is good because it spends less gasoline, but the thermodynamic reality is terrifying. The fuel in the combustion chamber not only serves to generate energy, but also fulfills an essential cooling function. Upon evaporating, the fuel absorbs heat from the cylinder walls and from the valves. A lean mixture lacks this cooling effect, which raises combustion temperatures to levels that exceed the metallurgical limits of the components. The first symptom of a sustained lean mixture is observed in the spark plugs. The electrodes, designed to resist extreme conditions, begin to suffer an accelerated thermal erosion process. In severe cases, the temperature is so high that the central electrode of the spark plug can reach its melting point, literally melting inside the chamber. This molten metal can detach and cause catastrophic damage to the cylinder walls or, worse yet, act as an incandescence point that causes pre-ignition of the fuel, a phenomenon that can destroy a piston in a matter of seconds. The exhaust valves are the next victims. Unlike intake valves, which receive fresh air, exhaust valves are constantly bathed in burning gases. A vacuum leak raises the temperature of these gases to the point where the metal of the valve begins to soften. This causes the valve seat to deform or the edges of the valve to burn, which results in a total loss of compression. Ignoring a simple hiss under the hood or a dried-out vacuum hose is, in essence, allowing an invisible blowtorch to work slowly in the heart of your engine, melting components that cost thousands of dollars for not having invested a few cents in a piece of new rubber. Error 2. Carbonization in direct injection valves. Technological evolution brought us direct injection gasoline engines, known as GD1, which promise greater power and lower consumption by injecting fuel directly into the combustion chamber instead of doing it in the intake port. However, this innovation introduced a design error that many owners are unaware of and that ends up suffocating the engine: the massive accumulation of carbon on the intake valves. In traditional indirect injection engines, gasoline-containing detergent additives constantly bathes the back of the intake valves, keeping them clean of oil and carbon residues. In a GDI engine, this never happens. The problem is aggravated by the positive crankcase ventilation system, which recirculates oil vapors towards the intake to be burned. These oil vapors come into contact with the intake valves, which are at extremely high temperatures. As there is no jet of gasoline to clean them, the oil cooks onto the metal, forming a hard and rough carbon crust that grows with every kilometer traveled. This process is insidious because it occurs gradually, stealing from the engine its volumetric efficiency. As carbon deposits increase, the geometry of the intake port is altered. The airflow, which should be laminar and fast for efficient combustion, becomes turbulent and restricted. It is like trying to run a marathon breathing through a straw full of sand. The engine loses power, the idle becomes unstable, and fuel consumption skyrockets because the computer tries to compensate for the lack of air by injecting more gasoline, which in turn generates more carbon, creating a vicious cycle of mechanical degradation. If a professional cleaning of these valves is not performed through methods such as walnut shell blasting or specific solvents every 60,000 or 70,000 kilometers, the accumulation can become so severe that it prevents the valve from closing completely. This generates misfires and can cause pieces of carbon to detach and fall into the cylinder, scratching the walls or damaging the catalytic converter. Direct injection is a marvel of engineering, but without conscious management of carbonization, the engine is condemned to a death by premature asphyxiation, becoming a shadow of what it used to be when it left the dealership. Error 1. The clutch habit and axial load. We reach error number 1, the most destructive and, paradoxically, the most common habit among drivers of vehicles with manual transmission: keeping the clutch pedal pressed while waiting at a traffic light or leaving the foot resting lightly on it while driving. This behavior is a direct attack against one of the most vital and least understood components of the engine: the crankshaft thrust bearings. To understand the gravity of this error, we must visualize the crankshaft. It is the master shaft that converts the vertical movement of the pistons into rotation. The crankshaft has a minimal lateral play, controlled by the thrust or axial bearings. When you press the clutch pedal, the hydraulic system exerts a massive pressure of hundreds of pounds to separate the friction disc from the flywheel. This force does not disappear into the air, it is transmitted directly to the crankshaft, pushing it towards the front part of the engine block. Thrust bearings are designed to withstand momentary axial loads during gear changes, but not to resist that pressure for entire minutes at every traffic light. By keeping the clutch pressed, you are forcing the crankshaft to rotate while it is being pushed with force against these bearings. The critical problem is that, at low idle revolutions, the oil pressure is minimal, which means that the lubrication film between the crankshaft and the thrust bearing is extremely thin. The result is premature wear due to metal-to-metal friction. Once the thrust bearings wear out, the crankshaft acquires an excessive axial play. This means that the crankshaft can shift forward and backward inside the engine. This destructive play alters the alignment of the connecting rods, causes leaks in the main oil seals and, in extreme cases, can lead to the crankshaft physically hitting the engine block or destroying the crankshaft position sensor, leaving the vehicle inanimate. The cost of replacing these bearings implies dismantling the engine completely, a repair of epic proportions that could have been avoided simply by putting the lever in neutral and releasing the pedal. This habit not only burns the clutch release bearing, it is, literally, trying to push the crankshaft out of the engine. Throughout this analysis of destructive habits and the engineering of neglect, we have seen how the daily decisions of the driver dictate the death sentence or the longevity of their vehicle. The automobile is not a static entity, it is a dynamic system of thermal exchanges, hydraulic pressures and micrometric tolerances that react to every stimulus. The master error of most owners is to see maintenance as an optional expense or a nuisance, when in reality, it is the only investment that guarantees the preservation of their heritage.